Peace be upon to you. So today we will try to explain about Runge Kutta. Our first article is Implicit Explicit Runge Kutta Methods for Time-Dependent Partial Differential Equation by Yuri M. Escher, Stephen J. Ruth, Raymond J. Spiteri. In this work, we consider problem of convection division type for ut equal to ux plus v delta u for v is bigger than 0. Discretization of the special derivative yields a very large ordinary differential equation system in time, which shown in 1.2, where f correspond to the convection or hyperbolic terms ux and g correspond to the diffusion or parabolic terms v delta u. We now develop some IMAX Kutta scheme. For G, we consider an implicit Estech-Dirk scheme with coefficient in the usual Butcher notation. Let sigma equal to s plus 1. For f, we consider an s plus 1 stage explicit scheme with the abscisse as shown, and the coefficient to cast the Dirk scheme as an s plus 1 stage scheme as well, we can pad the s stage scheme with zeros, which will yield us this table. Referring to this coefficient of the past table, we see that the value of c is equal. One step from Tn minus 1 to Tn equal to Tn minus 1 plus k of the IMAX scheme is given as follows. Set k1 equal to fun minus 1 for the value of I. Solve for ki, where ki is equal to gui, where ui are shown in this equation. We then evaluate ki plus 1 equal to fui, where un is shown in this equation. We consider two special cases, where the first case is shown here, where we will yield this equation. Next, this is the second case, where it needs to be evaluated. Furthermore, if in this example, we consider the case of 1.2 where u is equal to pq, f is equal to 0 f2 and g is equal to f1 0. Thus, we apply the implicit scheme to advance q and the explicit one to advance p. Moreover, if f1 is independent of q, then we will yield this equation. Therefore, the scheme becomes explicit. As shown before, using a centered discretization scheme for the special derivative of advection diffusion PDE, a non-Newman analysis yields that a simple yet appropriate test equation is the scalar ordinary differential equation with f equal to I beta u and g equal to alpha u, where alpha, beta are equal constant. Usually, alpha is less or equal to 0 and beta is bigger than 0 and I is equal to set negative 1. For a given time step k, we can define x equal to k alpha, y equal to k beta, and z equal to x plus iy, and write an IMAX step 2.1 to 2.2 as un equal to its equation where it's equivalent to rz un minus 1, where we can get the equation of ui for a given I. For scheme where sigma equal to s, an expression like 3.1 need not to be used because un is equal to us. Let us consider the two Euler scheme first. For the usual pair 1, 1, 1, 1, equation 3.2 implies un equal to 1 plus iy over 1 minus x un minus 1.
Now we are going to proceed on our next article, that is on the stability of implicit explicit linear multi-step methods by J. Frank, W. Hadsforder, and J. G. Viewer. In this paper, we are going to look at these general ordinary differential equation problems. There is W prime t equal to F t Wt plus Gt Wt, where t is bigger than 0. F represents the non-stiff parts and G represents the stiff part of the system. Here the term non-stiff is used in a loose way to indicate terms that may be solved efficiently in an explicit way. For the numerical solution of this equation, we consider implicit-explicit linear multi-step methods, as shown in the equation. From this equation, torque denotes the time steps and the vector Wn approximate the exact solution to Tn and T. In this article, we also discuss the stability properties of the scheme for the scalar. These complex test equations, that is W prime t equals to lambda Wt plus mu Wt. For the application of implicit-explicit scheme, the following substitution is done. There is lambda substituted with torque lambda and mu substituted with torque mu. The substitution then gives the following explicit-implicit scheme equation. Lastly, the article also discusses about stability, which is determined by the location of the roots of the characteristic equation. For stable equation, the root L must be higher than 1 with strict inequality for multiple roots. For this equation, use the explicit midpoint method to provide explicit part and implicit part. First of all, we divide the equation into three parts. There is a z equal to 1 over 2 times 1 minus z square. B z equal to z, C z equal to 1 over 2 times 1 plus z square. This three part is then substituted into this equation. This is the final answer of this example. It is negative I sin phase.